All right, so yeah, I just thought of that example, and I think it's interesting because they don't sort of give you enough examples of where the degrees are equal. And you sort of looking at this, it's not obvious that you should do long division. But the idea is if the degree of the numerator is greater than or equal to the degree of the denominator, then long division is going to be your method of choice here. All right, so how do I do that long division? I'm going to do the denominator divided into the numerator. I'm going to put in the plus 0x, although I probably won't need it. And then so x squared goes into x squared one time. I'm going to put that in my constant column because that's how I like to roll. And then I have x squared plus 1. I subtract, and I get 4. So that is going to be plus 4 over x squared plus 1. All right, so that's what I get by long division. Now, by the way, there is an easier way to get from this expression to this expression. If you just notice that if I have x squared plus 5 over x squared plus 1, then I could rewrite that as x squared plus 1 over x squared plus 1 plus 4 over x squared plus 1, right? Because I could combine these numerators and I'd get that, right? So then x squared plus 1 over x squared plus 1 is equal to 1. There you go. You don't even have to worry about x being 0 because x squared plus 1 is never 0. So there you go. That's another quicker way to get this result from here, but it only works because this polynomial rational expression is simple to work with. All right, so next let's see how to integrate that, because there's actually something in here that's going to be really useful for one of your homework problems. So I'm going to do my integral. I'm going to write this over again just because I've digressed. I have a tangent, a big long tangent in here. So I'm going to start tangential digression in here. So I'm going to restart the problem. So integral x squared plus, so that the person grading it doesn't get lost, you see. X squared plus 5 over x squared plus 1 is equal to the integral of 1 plus 4 over x squared plus 1 dx. All right, so then I can do the integral of 1. That's pretty easy. It's x, and I have integral of 4 over x squared plus 1 dx. Now, what am I going to do with this? I can't do du because du would be 2x. It doesn't match. I can't do partial fractions because the denominator does not factor. So we're going to use this. We used this trick before. We're going to use it again. We used it in the last problem. We're going to use it again. And this is the trick. Like, keep your eye on this because you will use this for number 9 in your homework. Okay. What I'm going to do as a separate step is pull out the 4. You're going to get used to not doing that, but for now I'm going to pull out the 4. And then, oh, look, I pull out the 4. Look, it's that again. Again, with the 1 over x squared plus 1. That comes up so frequently. It's a good thing that I noticed last time that the antiderivative of 1 over x squared plus 1 is inverse tangent of x. And now I've done my last integral, so I put a plus c. So very soon, you're going to be at the point where you just go straight from here to here. And you say, oh, I know 1 over x squared plus 1 is inverse tangent. We'll pull the 4 out. Boom. All right, there you go. For now, I wrote this out so we can see where that came from. That's another example. Keep your eye on this process right here because you're going to use it. Use this idea in page 369, number 9, the inverse tangent idea. All right, so with that in mind, here is your homework assignment, which I could have written out beforehand, but I didn't. We're doing chapter 6. This is your homework. Still jumping around section by section. The book's all jumbled up. Page 360. I say it is the book and not me who is jumbled up. Page 369, we're going to do number 1 through 21 of the odds. And you're also going to do the posted Rogowski 434, a mere 3 problems. But I like that Rogowski gave you more of the long divisions to do. Our textbook just hardly gives you any. I think it's like one of them in the entire book. All right, so there you go. That's your homework. That's the method of partial fractions. There's actually a lot more to partial fractions. You know, there's things that happen like what if you have, instead of, 2 factors that are different, what if you have 2 factors that are the same? There's the question of if you have quadratic factors that are not reducible, then instead of putting a or b in the top, you put like ax plus b. So there's actually a lot more that you can do with this, and in years where we're not as pressed for time, I usually do those. But for this year, especially given what's happened with our timing, I'm just really focusing on what is the minimum you need for the AP exam. So you should be aware that partial fractions, like it's a bit of a bigger rabbit hole to go down. If you want to see a little bit more of it, at least have a look. So this is just a suggestion. If you want to see sort of how this goes further, one thing to look at is page 371 of your textbook. Just look at number 47 and 48. It kind of they're homework problems that explain what you're supposed to do. Have a look at those. If you are interested in it, see me in Flex. But that's just something that you might want to look at. But even that, there's more to it. These rational expression integrals, it's huge. So I'm just sort of skimming the surface of that and getting the minimum that you need. All right, there you go. There's your homework. Goodbye.